But ultimately what we're going to use in this section here is, how do we locate the vertical and horizontal asymptotes and then put that together with some other pieces of analysis to sketch the graph. So the book gives you these kind of the 7-step process that you can go through, an algorithm, if you will, on sketching a rational function. Step 1 basically says find the domain. Right? So factor the numerator and denominator because remember the division by 0 in the denominator we don't want in the domain. Right? And then step 1 continues to say go ahead and find the y-intercept and plot it. Right? Well, step 2 says write the fraction in lowest terms and use the numerator to find the x-intercepts. Right? So basically we're going to find the x-intercepts of the graph from the numerator of the fraction. Right, and the next step would be step 3, we're going to find the vertical asymptote. So remember that comes from setting the denominator equal to 0. And remember what we talked about in the prior section, we got to make sure the fraction is in lowest terms. So you notice right here it says put it in lowest terms, right? Because we could have a hole in the graph, right? We don't see that often, but we did see that in one of the examples in the last section. So we're going to find vertical asymptotes for our rational function in step 3. Right, and then step 4 would be to find the horizontal or oblique asymptotes. Now remember, we're not going to cover oblique asymptotes, so step 4 for us would be find the horizontal asymptotes, right, again, based on the rules we talked about in the last section. Now, something new we're going to do here is step 5. So step 5, what we're going to do is we're going to basically plot some points around the asymptotes and the intercepts. We're going to find where our graph is above the x-axis and where it's below the x-axis. And we're going to illustrate how to do that in a second, and that's going to help us kind of fill in the shape of the graph. Right, and then step 6 is going to be to analyze the behavior of the graph near each asymptote. Right? Again, basically what we're going to do is plot some points to analyze the behavior, and we'll talk about that in more detail. And then step 7 would be put all the information together to sketch a detail of the graph. So let's take a look at an example where we illustrate these steps. So let's suppose we're looking at the rational function x minus 1 over x squared minus 4. Again, I want to remind you, I think I've said this quite a few times in this chapter, we have graphing technology that can graph these functions for us. And that's great, and we definitely want to use that graphing technology, right? However, one of the other things we're developing in this class is your tools of analysis, right? Your critical thinking, your quantitative reasoning, okay? So even though we have the graphing technology, we will use the graphing technology to check our work, but initially we're going to attack these problems by analyzing. Right? Besides, think about this, right? When the aliens invade Earth, because they're going to, it's going to happen, it's inevitable, right? When the aliens invade Earth, and you and Bruce Willis are saving the planet. Bruce Willis doesn't know any of this graph these curve sketching. And what's going to happen, inevitably, the aliens are going to challenge us to a graphing duel. So it's going to be you and Bruce Willis doing a graphing competition, graphing duel, and you're going to be totally prepared, right? Because they're going to take the graphing technology away from you. Those aliens are really smart. Right? I mean, they've mastered space travel, right? So you are going to be so prepared, and Bruce Willis is going to be extremely thankful that you can graph all these functions without technology. All right? So let's work on your ability to save planet Earth eventually when the aliens invade. All right? So step 1 for graphing a rational function was to basically find the domain, right? And part of that is going to be factoring the numerator and denominator, and then we'll find the y-intercept. So for this example, if I factor the numerator and denominator, right, it's going to be x plus 2 times x minus 2 in the denominator, right? So the domain then is any real number as long as x is not negative 2 or positive 2. The second step here says find the y-intercept. So I'm going to plug x equals 0 into the equation. And if I plug x equals 0 into the equation, I basically just get negative 1 in the numerator, negative 4 in the denominator. So I get a y-intercept of 1/4. All right, and then the next step 2, is to find the zeros of the denominator. Right? This is going to lead us to the vertical asymptote. Excuse me, that's zeros of the numerator. That's going to lead us to the x-intercept, right? So if I come up here and I set y equal to 0, it doesn't matter what happens in the denominator. All right, the denominator gives me division by 0, which is vertical asymptotes. So when I'm finding x-intercepts, I'm going to find the zeros of the numerator. So I set the numerator equal to 0, and I get x equals 1. All right, so my x-intercept for this particular example is at x equals 1. All right, now step 3 then is to find the zeros of the denominator, right? And this is going to give us our vertical asymptotes. So if I take the zeros of the denominator, I get asymptotes of -2 and 2. Now remember, there's no holes in this graph, right? Because neither of these factors in the denominator cancel with the numerator. So because both of these, survive, they don't get canceled out. They are my vertical asymptotes. All right, now let's suppose we stop for a second and we're going to plot this information on a graph. So I'm going to plot my vertical asymptotes, I'm going to plot my x and y intercepts, and here's that information so far, right? So here's my 2 vertical asymptotes. I'm going to put as dotted lines. Remember, they're not really a part of my graph, so I'm going to dot them. And then here's my y-intercept and my x-intercept. And we want to gain some more information here. We want to find the horizontal asymptote, and we also want to start to kind of analyze what happens to the graph, right? And what I mean by that, for example, right, as I get close to this asymptote from the left, is the graph shooting up to infinity or is it shooting down to negative infinity? We're going to figure that out in just a second, right? All right, so step 4 says locate any horizontal asymptotes. So remember what we talked about in the prior section. We compared the degree of the numerator to the degree of the denominator. So in this case, the numerator's degree is 1, the denominator's degree is 2, and so that tells us that y equals 0 is the horizontal asymptote. All right, now step 5 is the new step in this section, right? So basically what we're going to do is use the zeros of the numerator, right? Those are our x-intercepts, and the zeros of the denominator, those are typically our vertical asymptotes. We're going to break the x-axis into some intervals. And what we're going to do is we're going to plot points around each of those values, right? So let's see what that looks like. So here's the x-axis for my graph, and I'm going to plot the vertical asymptote of -2. I'm going to do this chronological from smallest to largest, right? So from left to right. So I got -2, then I have my x-intercept of 1, and then I have my vertical asymptote at 2. Basically what I'm going to do is I'm going to fill in the gaps. So again, if I look back at this graph here, right, what I'm going to do is I'm going to come over here to the left, I'm going to plot a point. I'm going to, in between this x-intercept and this vertical asymptote, I'm going to plot a point. And then between this x-intercept and this vertical asymptote, I'm going to plot a point. And then to the right of this vertical asymptote, I'm going to plot a point. That's basically what we're going to do in step 5. So if I come back to the screen, we can see, right, to the left of -2, what we've kind of identified what that interval is, right? So from negative infinity up to -2. In that interval, I'm going to choose x equals -3. Now, I want to point out to you, I could pick any x value. I could pick -3, -4, -5, -10. Right? I could pick any x value I want, as long as it's to the left of this asymptote. So I take -3 and I plug it back into my original equation here, my rational function. If I plug -3 into there, I get -0.8 as a result. So what that tells me is it's below the x-axis. It's got a negative number. It's below the x-axis. And I'll plot that point in just a second on the next screen. And let me continue with this process. So between the vertical asymptote and the x-intercept, I'm going to plot a point. Now technically, I had already plotted a point. Between -2 and 1, I had plotted the when x was 0, the y-intercept. So I'm just going to use that point. Right? So I'm going to use that point, the y-intercept, and there's the point I'm going to graph. Right? All right, then I'm going to look in the next segment. So from the x-intercept to the vertical asymptote, right? So I'm in the interval from 1 to 2. As x goes from 1 and x goes to 2, I'm going to pick any x value in this interval. Right? I picked 1.5 as the x value. Plug it into the original equation. I get a y value of -2/7, and so that's a negative value, right, below the x-axis. So I'll plot that point in just a moment. And then our last segment to the right of the vertical asymptote. So I'm going to pick x equals 3. Again, I could pick in this interval from 2 to infinity, right? From 2 to infinity, I could pick any x value. I'm going to pick x equals 3. So I plug 3 into the equation. I get a y value of 0.4. Noting to myself that's above the x-axis, that's the point that I'm going to plot. So let me plot this information. Let me plot these 3 points on the graph that we found in each of those segments. Right? So here's the point we plotted to the left of -2. Between the x-intercept and the vertical asymptote, we had already plotted the y-intercept. Right? Between the x-intercept and this vertical asymptote, we plotted an additional point at 1.5. And then, but to the right of the intercept, we plotted the point x equals 3. And then we also, on that prior screen, found the horizontal asymptote. So here's the horizontal asymptote of y equals 0. So we're adding that information to the graph. All right, so on another screen, I just kind of put all of this together, right? So here's the points that we plotted. You know, here's that information that we had from plotting those points. And then I'm just kind of pointing out to you, right, that these 2 points are obviously going to have to connect to each other. So my graph is going to come through my x-intercept in this fashion. Right? So the last step we really want to take, right, is kind of what we talked about. What is the behavior going to be near each intercept? So again, near each asymptote. So again, if I look at, let's say, this vertical asymptote right here, if I move just to the left, is the graph shooting up to infinity, or is the graph shooting down to negative infinity, right? And basically this point here tells us that the graph is going to come from here to here and it's going to shoot down. Right? Now the reason that I know that's the case is if the graph was going to turn around and shoot up, I would have found an x-intercept right here, and I don't have an x-intercept there. All right, since I know that's not the case, I'm going to come back and kind of erase that for just a second. So I know the graph isn't going to shoot upward. I didn't find an x-intercept there, right? That's how it's going to behave. Right, and then ditto on the other side of the asymptote, right? So if I step just to the right of that asymptote, is the graph going to shoot up or is it going to shoot down, right? And because I have this point that I plotted, I know the graph is going to shoot up, right? Again, it's not going to shoot down because I would have found an x-intercept here. So this is the whole reason for plotting some additional points. It's our analysis and determining how the graph behaves near the intercept. All right, so let's go ahead then and jump to the next screen and just kind of point out to ourselves that's what we're looking at here, right? So based on the information that we have, the points that we've plotted, right? Based on this point, we know the graph is going to hug the horizontal asymptote from below. And then we know it's going to shoot down to this vertical asymptote. Those all have to connect to that point we plotted. Then if I look back at this y-intercept, I know the graph's going to have to shoot up. I know that it won't shoot downward because I would have found another x-intercept here, and I don't have one. And then I know these have to connect and shoot down, right? And then this point tells me I'm going to shoot upward, and then I'm going to hug the horizontal asymptote from above. So putting all that together, there's the sketch of that rational function. Now, we just walked through an example where we did some very deep analysis here, right? This is excellent, right? This takes time to practice this. And then at this point, we want to take out our technology and check our work, sketch the graph and check our work. All right, so if I pull up Desmos real quick and plug that rational function in, right here's the same graph that we're seeing on our notes, right? We have those vertical asymptotes of 2 and negative 2. We see the horizontal asymptote of y equals 0. We can even see our y-intercept and our x-intercept there. All right, let's take a look at another example here. This one's a little bit more difficult. All right, suppose we want to analyze the graph of this rational function. So first thing we're going to do is find the numerator, factor the numerator and denominator, right, and plot the y-intercept. Right? So factor the numerator and denominator. So that shows us that the domain can't include 2 and negative 2. And then if we plug in x equals 0, I like to come back to the original equation. If I plug 0 in here, 0 in here, I just get a 2 in the numerator and a negative 4 in the denominator. So that gives me a y-intercept of negative 1/2. Step 2, right, find the zeros of the numerator. That's going to produce our x-intercepts for us. Now, one thing we want to be a little careful of here at this point, we want to make sure that we don't say x equals 2 is an x-intercept, because notice it's going to cancel with the denominator, right? So we're going to wipe those guys out, and we're going to say 2x minus 1 equal to 0 gives us the x-intercept of 1/2. And then also when we do step 3, right, finding the vertical asymptotes, remember we're not going to say x equals 2 is a vertical asymptote, right, because it canceled out. So the only vertical asymptote is going to come from x plus 2 factor, and there's our vertical asymptote. All right, now, since we're talking about the division by zeros, right, the vertical asymptotes, let's remind ourselves that x equals 2 is a hole in the graph. right? So x equals 2 would be a hole in the graph. Now, how would we find the y value? Well, in fact, here's what I would do. If I plug 2 into here, I'm going to get 4 minus 1, which is 3 in the numerator, and then 2 down here gives me 2 plus 2, which is 4. So if I could plug 2 in, keep in mind I can't, it's not in my domain, but pretend that I could, I'm going to get 3/4 as the y value. And what that tells me is the whole has a y value of 3/4. So if we plot all of this stuff on a graph, right, here's what we see, right? We see the whole at 2, 3/4. That's where it wants to live, right? Here's our x-intercept, our y-intercept, and then here's our vertical asymptote, right? So far our analysis has produced this for this graph. So then let's go on to step 4. So step 4 is find the horizontal asymptote. So again, in this case, we have the numerator and denominator having the same degree. So we'll take the ratio of the coefficients. So y equals 2 over 1 is the horizontal asymptote in this case. And then step 5, again, is that new part. That's where we're going to plot a bunch of points around the graph. Now, I came back to the graph real quick just to point out to you again, here's our approach. We're plotting points around what we have on our x-axis. So we have a vertical asymptote here on our x-axis. We're going to plot a point to the left of that. We're going to plot a point to the right of it. But we're going to make sure we stay between this x-intercept and the asymptote. And again, just point out to you, we've already plotted a point there, right? So we're just going to steal that one and use it. And then we're going to plot a point to the right of this x-intercept. And we can't really use this point, right? So we'll plot a couple other points over there. All right, so again, to the left of -2, here's the interval that we're looking at from -infinity up to -2. I'm going to pick -3. So when I pick -3, you plug it in the equation, I get a y of 7. So that tells me that it's above the axis at the point -3, 7. We'll plot that on the next screen. Then I'm going to look between -2 and 1/2, right, my x-intercept here. So here's the interval from -2 to 1/2, and I'm going to pick any number in that interval. Looks like I picked -1. I didn't use the y-intercept here. So pick -1, find the value of -3. The advantage to that, it gives me an additional point to plot. So instead of just plotting the y-intercept, I'm now plotting an extra point. Always good to have some extra points there. Then between the x-intercept and the whole, I'm going to go ahead and plot an extra point. Right? So in the interval 1/2 to 2, I'm going to plot x equals 1. That's above the axis at 1/3. And then to the right of the whole, from 2 to infinity, I'm going to plot x equals 3. And that's a y of 1, and that's above the x-axis. So if I take those points that I plot, right, and I put it on my graph, right, here's the points that we determined. Right? So here's the point -3, 7, and then here's the other points that we plotted here. Okay? And again, here's the beauty of now plotting these points, right? I'll kind of connect the dots, right? So I know that at this point, the graph is going to shoot like upward along the asymptote here, and it's going to come downward to the horizontal asymptote. Okay. Now again, I know that out of this point, I'm not going to shoot downward along the asymptote to -infinity because I would have found an x-intercept here. I don't have one there. So that point tells me what the shape of the graph looks like over here, and we continue in that fashion, right? So putting all this information together, right, we can see what the graph is going to look like based on those additional points that we plotted. Right? Now again, this is the analysis that we go through. Right? We could bring up our graphing technology and check our work. And just for the sake of time, I won't bother to do that in this example, but I strongly encourage you to take out your TI calculator or go to Desmos and graph this equation to see your analysis was correct. All right, this next problem we're going to look at is actually it's pretty cool. This is like a problem-solving type of problem, and it really tests us on our tools of analysis. And what I mean by that is, in this problem, we're being given the graph of a rational function, being asked to build the equation. All right, so we've got to really use our tool of analysis in a unique and creative way. So first thing I'm going to focus on is the vertical asymptotes. So I'm going to notice there's a vertical asymptote at -5. There's a vertical asymptote at 2. So that corresponds to division by zeros. So I know initially my equation has to have the factor x plus 5, so that negative 5 will give me division by 0 here. And it has to have the factor x minus 2 in the denominator, so that x equals 2 will give division by 0. Now, one thing that I notice here, and we kind of talked about in the prior section, something really interesting, right? So here the graph kind of bends in different directions, right? So just to the left, the graph is going off to infinity, and just to the right is shooting down to minus infinity. And remember what we talked about in the prior section was that when the multiplicity of that factor is odd, that will occur. So this factor needs to have an odd exponent. And it already does. It has an exponent of 1. I could make it an exponent of 3 or an exponent of 5 or 7 or 9. But an exponent of 1, we'll just keep it the smallest possible odd number. Right? Now at this asymptote, notice that the graph just to the right shoots down and the graph just to the left shoots down. So in that case, I have to have an even multiplicity. Remember when we talked about that, right? So that has to be an even multiplicity there. And so this exponent over here needs to be a 2 or a 4 or a 6 or an 8. So I'm going to go ahead then and make that one a 2 and leave that one a 1. All right, now the next thing that I'm going to analyze here is let's say the x-intercepts. Right? So I know the x-intercepts come from the zeros in the numerator, like we talked about in the prior two examples. So I see an x-intercept here of negative 2, and I see an x-intercept of 5. Now again, notice this x-intercept is bouncing, so it has to have an even multiplicity on its factor, and this x-intercept is crossing through, so it has to have an odd exponent, an odd multiplicity. So I'm going to go ahead then and make this an even exponent, so that at negative, I think I did that wrong, didn't I? Is that 1, 2, 3, 4, 5? Yeah, that should be an x plus 2 in that factor. All right, I'll fix that before I print these out to you. So this would be an x plus 2 squared here, and then this would be x minus 5. Right? So x plus 2 squared, again, even multiplicity because it's bouncing, and then x minus 5 to the 1, odd multiplicity because it's passing through. All right, then the last thing I'm going to take into consideration here is the horizontal asymptote. So I have a horizontal asymptote of y equals 2. Now if I look at this example that I have here, even with the typo, what I'm going to get if I multiply all this stuff out, the leading term is going to be x squared times x cubed. That's going to be my leading term. And down here I'm going to have x times the x squared, and that's going to give me x cubed. So the horizontal asymptote of this function, since the numerator's degree and denominator's degree is the same, this horizontal asymptote is going to be the coefficients, 1 over 1. So this equation isn't exactly correct in the sense that the horizontal asymptote is not right. So I need to put a 2 in front of here. And if I have 2 over 1, then the horizontal asymptote would work. All right? So I'm going to go ahead then and I'm going to put a 2 in front of the numerator so that we then match the horizontal asymptote. All right, and then just checking my work, right, bringing up Desmos, plugging in the correct equation where I fixed that typo there, right? I see that I'm getting the same graph that I got from what was given to me, right? So here's the graph that's given to me, and if I bring up Desmos, I can see I'm getting the exact same graph there. All right, so those are kind of cool problems because they're testing my analysis ability, and I've had to build the equation based on the behavior I saw in the graph. Okay, so last example, we're going to look at some word problems. We're going to look at applications of rational functions. So this one application we're going to look at, I don't want to spend too much time on this. You're definitely going to get practice on this in my math lab, right? But let's at least do one application together. So in this application it says that Reynolds Metal Company manufactures aluminum cans in the shape of a cylinder, so like a Coke can, and it has a capacity of 500 cubic centimeters. So the top and bottom of the can are made of a special aluminum alloy that costs 5 cents per square centimeter, and the sides of the can are made of a material that costs 2 cents per square centimeter. Now, letter A says express the cost of the material for the can as a function of the radius r of the can. So let's visualize our can for a moment. All right. So if we look at our can for a moment, we have a right circular cylinder, And so in essence, the top and the bottom are circles. So here's the top. The circle has an area of pi r squared. And here's the bottom, pi r squared as well. Right? Now the side of the can, this is pretty cool. If I take the side of the can and I kind of like cut it open and lay it out, it's a rectangle. So the area of this rectangle is, let's call it length, times width. So the length of this rectangle is actually the circumference of the circle, right? If I curl that rectangle back up, the circumference of the circle right here is 2 pi r. And then I have the height of the can is the width dimension right here. So the area of the side is 2 pi rh. So I need to take the total area of the top and bottom, and I need to multiply it by its cost. And then I'm going to take the total area of the side and multiply it by its cost. So first of all, the area is the two circles. So I have the pi r squared, one for top and one for bottom. And then I have the rectangle, which is the side of the circular cylinder. And then again, the cost is going to be, I got to multiply the 5 cents to the top and bottom, and then the 2 cents to the area of the side. Right? Now, the question here, the part A, direction, says express the cost as a function of the radius. So just like we talked about in 3.6, the problem here is we have height in our equation. I don't have just r's. So I have to get rid of the height here. Right, so I have to go back up in my problem and I have to look for some information that's going to allow me to tie height and radius together. And what's given to me in this case is that the volume is 500 cubic centimeters. So I'm going to use that idea of volume being 500 cubic centimeters. Remember, the volume of a right circular cylinder, I could look this up, I can Google search this, or it's in the front cover of my book. But the volume of a right circular cylinder is pi r squared h. So I'm going to set my volume equal to 500, and then I'm going to solve for h. If I solve for h here, and then I'm going to plug this h back into my equation. So if I plug that h back into my equation, here's the cost purely as a function of radius. Okay? And then I'm going to go ahead and simplify a little bit, right? So I'll just point out to you 2 times 0.05 was the 0.1 that I got here. 2 times the 0.02 is the 0.04. And then I'm going to simplify a little further. The pi's will cancel here. And then one of these r's will cancel in the denominator. And I clean up my cost function. And there's kind of my cleanest form. There's the simplest form of the answer for part A. Here's the cost as a function of the radius only. Now, there was a part B, a C, and a D to this question. And part B was like graph that cost equation. Part C was find the minimum cost. So let's do that on the next slide. So I'm going to take my cost equation. I'm going to graph it. So here's my cost equation. And keep in mind, if I'm plugging in my calculator, I'm using y's and x's, right? And probably on Desmos, I'm going to use y's and x's as well. So I did it on the graphing calculator and did a screenshot, and I found the minimum value. So here's the minimum value. So this is telling me that remember the x's are the radius. So this is telling me if my radius is 3.17, let's round, right? So if my radius is 3.17 centimeters, then the minimum cost, remember the y values on this graph are cost, right? My minimum cost will be 9.46, right? So if my radius is 3.17 centimeters, then my minimum cost will be 9.47 if I round.